Hello friends, subscribers and new viewers of this channel, and welcome to Control Engineering, Robotics and Mechatronics tutorials. In this tutorial we explain how to generate nice looking body plots of transfer functions in Python. To generate body plots we will be using the SciPy Python library, and believe it or not, this very powerful library has even functions to define transfer functions and to generate body plots. And over here as an example you can see a simple transfer function with 1 0 and 1 pole, and over here you can see the magnitude and the phase plots. I will teach you how to generate these plots and how to embed these two plots in a single figure, as well as how to save these figures in a PNG or some other graphics file such that you can use it in your student report or a scientific paper. Okay, let's start. The first step is to install the necessary modules and packages and to open your favorite Python editor. In my case, I will be using Anaconda and the Spider Python editor. Consequently, I need to open Anaconda Navigator. I will click on Start and search for the Anaconda Navigator. If you don't have Anaconda Navigator installed on your system, don't worry. I created a separate video tutorial explaining how to install Anaconda Navigator. A link to that tutorial will be given in the description below. After you open the Anaconda Navigator, you need to click here on the environments, and over here click on the base or the root environment and be patient until this environment loads with all the modules installed over here. So be patient. Then click here and click Open Terminal. In this terminal we will install the necessary packages. First of all, let's make sure that SciPy is installed. To do that, type pip or pipe install SciPy. And as you can see over here, SciPy is already installed. However, let's then make sure that matplotlib is installed. Let's just type pip install matplotlib, and you can see in my case it's already satisfied. However, in your case you might see the installation progress. And finally, let's make sure that we have numpy installed by typing this. Okay, good. Now we installed the 3 necessary packages. So close this terminal, then click here on Home and start Spider. I like Spider a lot since it's very easy to debug the code and to execute the code piece by piece in Spider. It also reminds me of MATLAB. Over here I will click on Cancel, and over here click to open a new script, and let's start with coding. The first step is to import the necessary libraries, modules and packages. First of all, we will need the plotting library. That is, we need to import matplotlib. So let's do this. Import, let me enlarge this, matplotlib.pyplot as plt. Okay, then let's import from SciPy signal. This library is used for signal processing and for control system design. And finally, let's import numpy. Import numpy as np. And let's evaluate this to make sure that we can actually import these packages. Good. Let's continue. The first step is to define our transfer function. Over here, for simplicity, I will assume a relatively simple form of a transfer function. However, in your case, you can choose any transfer function you wish. So here's my transfer function. It's going to look like this. W of s is equal to s plus 0.1 over s plus 0.01. And let's learn how to define this transfer function by using this very useful library Signal. Okay, to define our transfer function, we need to write. First of all, we need to name our transfer function. I will call it TF1. And then we need to call signal.TransferFunction. And here it is. So over here, we need to specify two things. We need to specify the coefficients of this polynomial in the numerator and the coefficients of this polynomial in the denominator. And they should be specified as lists. That is, they should be specified like this. Okay, so what are the coefficients of the polynomial in the numerator? The coefficients are 1, then comma, 0.1. Then the coefficients of the polynomial in the denominator are similarly 1, and then I have 0.01. Good. Let's evaluate this and let's see the output. So if I type now TF1 over here, you can see that my transfer function is defined. And you can also type print TF1. Good. To generate the body plot, we first need to define the frequency points. In body plots, the frequency is usually plotted in the logarithmic scale. Consequently, we will have to define a set of points that are defined over the logarithmic scale. And for that purpose, we will be using numpy.logspace function. However, to use this function, we first need to define the start frequency exponent and the end frequency exponent. So here is the start frequency exponent. It's going to be SF start frequency E. Let's call it like this. And I will start from 10 to the minus 4, and consequently over here I just need to write the exponent. That is my frequency for plotting. The body plot will start from 10 to the minus 4. The upper limit will be 10 to the power 1. So let's define the end frequency exponent to be EFE, and let it be, for example, 1. This means that this frequency will be 10 to 1. And let's just denote it here. This will be 10 to 1, and the start one will be 10 to minus 4. Good. Next, we need to define a number of frequency points. That is, number of frequency points between 10 to the minus 4 and 10 to the power 1. And these frequency will be equally distributed across this logarithmic scale. So let's, for example, assume 100 points. And let's define the frequency points. I'm going to call this array or list as W, and then I need to call numpy.logspace, and then I need to specify this. I need to specify my start frequency exponent, end frequency exponent, then I need to specify num to be number of points in between, and I need to specify the base. The base will be 10. That is, this is the base for this exponent. Okay, so let's evaluate this and let's see what will happen. And if I type W here, let's check. Okay, I see that the end frequency is 10 to the 10 and the first frequency is 10 to the minus 4. Perfect, we are ready to continue. And now we are ready to generate magnitude and phase functions. To do that, we need to use signal.bode function. Okay, the first input or input parameter of this function is our transfer function. So let's put it here. And the second input parameter is actually this vector W containing the frequency points. This function returns three things. It returns the frequency array, and this frequency array will be equal to W. We will denote it by WR. Then it will also return a log magnitude. So I will type log magnitude. This is the magnitude expressed in decibels, and this log magnitude is defined as 20 log of m, or basically 20 log of m, that's it. And it will return the phase. Okay, so let's evaluate this and let's see the output. So we will see first of all the frequency array. We see that this frequency array is exactly the array specified in W. Then here's our log magnitude. And we see also the phase. The phase is actually in degrees. So keep in mind this. Log magnitude is in decibels and phase is in degrees. The next step is to plot the log magnitude and phase as a function of the frequency. And here's the script I've wrote that will perform that task. Here it is. First of all, we need to define the figure. We need to specify the figure size over here. Then we need to call this function plot.semilogx. This function will plot on the x-axis the frequency points in the logarithmic scale, and then on the y-axis we will plot log magnitude. We need to specify the color to be blue, line width to be 3, and the style to be solid line. Then I will specify the label. The label will be frequency in radians per second, and I'm specifying the font size. Then I'm specifying the y-axis label. It's a magnitude in decibels, and I'm specifying the font size. And over here with this function tick params, I'm actually specifying the size of the font that's used to denote the numbers on the x and y axes. And over here I'm plotting the grid and I'm saving the figure. I will be saving the figure as the file magnitude.png with the dots per inch resolution of 600. I suggest you that you use at least 400 dots per inch. Okay, so let's evaluate this and let's see the output over here. And voila, here it is. Looks amazing. Looks really nice. Now, nice thing is that this file is actually saved in this folder. Here it is, and you can open it and you can add it to some other document, to your student report, or to something else. For example, to your website. Okay, let's plot the phase. Again, I'm defining the figure. I'm using semilog x. On the horizontal axis, I'm plotting WR. On the vertical axis, I'm plotting phase, specifying the color, line width, and the line style. Then I'm specifying the X label, Y label, and font sizes for the numbers on the X and Y axes. Then grid and save the figure. So let's evaluate this and let's see the output. Here it is. This is our phase. Looks amazing. And here's the saved graphics file. Looks very nice. Now, the issue with these two plots is that they are separated. Next, let's learn how to generate a single graph with the two subplots. To do that, here's the script I wrote. First of all, we need to use the function subplots. Then we need to specify the dimensions. Our subplot will have 2 rows and a single column. And we need to specify the figure size. Then again, to refer to the first graph, that is to the upper graph, I need to use AX0. Then I'm using semilog x. I'm specifying the frequency, log magnitude, color, line style, and line width. Then I'm setting the Y label, I'm setting the font size, and I'm setting the grid. Then the bottom graph will contain the phase. So I need to specify WR, phase, color, line style. Then an X label, I need to specify Y label, font size, grid, and finally I need to save the figure, and over here I need to specify the resolution. I like 600 dots per inch. Now, notice one thing over here. Here I commented the X labels for the upper graph. I don't need it since the labels are actually the same for both graphs, at least the horizontal labels. So let's evaluate this and let's see the output. And after some time, here's our graph. Looks amazing. Now they share the horizontal axis and we can see frequency over here, we can see the magnitude, and we can see the phase. And let's double check that our graph is properly saved. Here it is, and looks really nice. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and see you in the next video tutorial.